that.
You start recording it, okay.
Okay. So hello everyone. Good evening, good afternoon, good morning, wherever you are. This is the GeoVirtual 3.0 in the third version of GeoVirtual and GeoTalks organized by Gulf Geotechnical Engineers. If you are new to the Gulf Geotechnical Engineers, please do subscribe to our YouTube channels and our LinkedIn group. We do a lot of activities and online events and participate in many conferences. So hopefully you can find it useful. I will not introduce myself. If you want to know about me, please do check my LinkedIn profile or GeoStructure. I will introduce Dr. Marwan in a bit, and he will introduce the event as well.
Yeah.
I know most of you are excited about this event for geotechnical design and softwares and numerical methods other than the finite element. We have been around working with finite element for quite some time now, and especially in the Gulf region. But as designer, you should also know the emerging and evolving technologies and methods in the numerical design and numerical methods way far beyond the finite element modeling, as you will see from our experts today. So the stage is yours, Dr. Marwan. So Dr. Marwan is well-known figure, but for those who don't know him, he is the Senior Geotechnical Manager in Dubai Development Authority. He is the Vice Chair for Geotechnical and Material Engineering Committee at the Society of Engineers in UAE. He is also adjunct faculty in some universities in Abu Dhabi and UAE, as Hirwat Abu Dhabi and Abu Dhabi University. The stage is yours, Dr. Marwan. Thank you.
Thank you, Hamza. Good evening, everybody, or good morning, depending where you are, or good afternoon. Thank you, Hamza, for your effort, and thank you for our esteemed speakers, Dr. Ahmed Elkadi, Dr. Ahmed Amir, as well as Dr. Reginald. We will start with our keynote speaker, Dr. Ahmed Elkadi. First of all, we have now our GeoVirtual 3.0, which is related to numerical method in civil engineering and ground engineering, specifically geotechnical engineering. Practically, we have previously 3 geotechnical or GeoVirtuals, as mentioned by Hamza. Is a collaboration between the Gulf Geotechnical Engineer platform as well as the Society of Engineers in the United Arab Emirates, ISSMGE UAE Chapter, and ISSMGE as well in general. So thank you, Hamza, for your effort on that. I will start introducing Dr. Ahmed Elkadi. Dr. Ahmed Elkadi is a chartered engineer and researcher over 30 years experience, and he holds his BSc in engineering from Cairo University in 1991. His master and PhD for civil engineering, specifically in geotechnical engineering, from Delft University in Netherlands in 2000 and 2005. Dr. Ahmed Elkadi has experience in consultancy as well as in research and development. He worked for Delft and for Dutch Institute of Deltares, which we call it in Delft, basically, as well as previously he worked in Guyana, and he has extensive researches in numerical modeling and all type of modelings, which we are planning to discuss it today. So Dr. Ahmed, the floor for you, and you can start your presentation. Looking forward for the other speakers as well. Thank you.
Thank you, Dr. Marwan. Thank you, Engineer Hamza, and thank you, the Gulf Geotechnical Engineers, for the kind invite. Also, thank you for the co-presenters and for the audience for being here today. I will share my screen and then we start talking a bit. So the title of my talk in the coming 20 minutes will be a bit focused on what we call the material point method. The other title, Advanced Computational Techniques, is I think that governs maybe the meeting today. We're not looking only at finite elements, we're looking at other alternatives to complement finite elements. So they are not to replace finite element, but to complement finite elements. And I will dig a bit deeper into this. On the title page, you see experimental work, and that's something also I would like to come back during the presentation. Numerical and experimental going hand in hand. So that will also be my advice at the end, and that's why I show a bit of a complex experiment we do here at Deltares with a wave flume, where we can generate waves of 4 meters high, and this is a model of a pile impacting, so the wave is impacting this offshore pile, and we can look at scour and a scour mitigation measure, just to keep in mind. One slide or two on Deltares. So the Deltares is an applied research institute based in the Netherlands. And applied is important because that differentiates us from the university. We are looking really at translating fundamental research into applicable, let's say, solutions. We work worldwide. Our focus is water and subsurface and infrastructure. So deltas, coastal areas, these are our main focus and knowledge. In numbers, we are about a bit more than 900 employees work for Deltares, mainly in the Netherlands. We have 2 offices in Delft, where I'm sitting now, and in another city called Utrecht. I shared this photo, excuse me, from our campus last week. So we were hit with a snowstorm last week, and this is how the campus looks like today. Is completely gone, so it's not snowy anymore. The Deltares and predecessors are a bit more than or nearly 100 years old. And as I mentioned, we have numerical as well as experimental facilities, expertise in water and subsurface. Moving into our topic, because I'm starting the first presentation, I thought, okay, when we talk about geotechnical engineering, we are known as geotechnical engineers to be more of the use of empirical and semi-empirical approaches for all good reasons, a lot of uncertainty, but a lot of expertise and history as well. And that is, of course, okay to a certain extent, to a certain limit. We make use of what is known as limit equilibrium methods, for example, for slope stability, and also sometimes for bearing capacity, where you also deal or simplify actually the problems and the world to a certain extent. And we have simplified soil models. We use finite element for quite some time now, but the utilization of finite element varies a lot, from simple use with simple models to very complex applications. We know the one-dimensional consolidation theory and settlement methods. We rely also to a certain extent on manual calculation, and altogether lead to one way or the other to conservative design. We have to simplify the complexity we are dealing with to a certain extent, and sometimes oversimplify. So we have to deal with uncertainty in what we call them the safety factors, over design, and that is not more actually going hand in hand with neither the complexity we face today, nor the resilience we aim at, nor the circularity and the, let's say, the lack of resources that we are facing nowadays in our world. So when we look at where we stand, we know that we are dealing with actually much more complex designs and situations in our day-to-day business as geotechnical engineers now. Urbanization is one example. We have much more complex structures, much more complex soil structure interaction also with the surroundings. Soil has been never simple or homogeneous. We always deal with nonlinearity and heterogeneity. And we need to be more realistic in our modeling approaches. So we need to look at actually how we model our projects and our soil and soil structure interaction. So to get into a realistic approach, we utilize numerical methods for quite some time. Of course, finite element stands out in this case as one of the major numerical method being utilized. where we can capture nonlinearity. In some of the tools we have, we can look even at cracking if we are dealing with some structural material plasticity, soil structure interaction. By that, we can identify where it actually a risk is, excessive deformations, failure patterns, and so on. And we also can move forward with value engineering if we need or we would like to. So this is where actually the added value of numerical methods comes in, compared to what we have seen on the previous slides of the a bit more simplified methods that we are used to use. We see also that we are more and more facilitating, or we are aiming at resilient infrastructure, and that also comes with the optimization and the value engineering. And we need to have a clear role in how to utilize these numerical methods to support sound decision making. So we need to support this informed decisions on visibility, on the risk, on constructability, and definitely to try to mitigate over design and waste of resources. Here I tried to give a glimpse of the numerical methods at hand at the moment in geotechnical engineering, and that's not all, but the ones that at least we most use, and some of them will be discussed today. So I mentioned already the finite element method, the most widely used for continuum problems. It's the workhorse, let's say, of numerical methods in geotechnical engineering. Can do a lot, can also help us a lot with our problems. But in certain problems, in certain mechanisms, it comes short. So there are some limitations that we need to realize and deal with. But in general, it's quite applicable and can also be applied in many cases. I mentioned the limit equilibrium method, so we need to mention it again. It's still applicable, still can be used. Boundary and analytical element methods when we're dealing with boundary dominated problems, and it will be discussed today, so I will not go deep into that. We have experts on the topic, and also in combination with, some of these methods can be combined with, for example, finite element method, and that adds value and makes our solution even more stronger. Discrete element methods, and I had the opportunity to experience it in my PhD, where we can really model, let's say, discontinuities when we are dealing with particles or blocks, so fracture of rock, or in some cases concrete, can be captured very well. It is computationally heavy, as far as I can recall. Maybe there are new developments there, and also in the hardware, of course. But it's very valuable for certain mechanisms, certain problems, also in combination, coupled with maybe another solution. And the focus today of my talk, at least, is the material point methods for large deformation and moving boundaries. And I'll talk a bit more on that in the coming slides. So why we are looking to something next to finite elements, we said already, yeah, in some mechanisms, in some situation, finite elements will come short. We know with large deformation, you get mesh distortion. Remeshing is quite, well, I would say difficult. It takes time, and it's not always successful. And in that case, you need an alternative. We also talk about boundary problems. We can talk about discrete problems where finite elements really cannot help us, or it has to be combined with something else. Moving interfaces, and I will give an example of a pile installation, for example. You have to make tricks, actually, if you want to come close with finite element. Although there are alternatives which can actually model this moving interface more realistically. And that can be in a pile installation, can be also when you're close to failure or in a failure. Like the embankment we look at now, onset of failure you can capture maybe with finite element, but if you want to see what happens afterwards with this large deformation, it's very difficult to get that properly with finite element without going into remeshing and mesh problems. So the continuum is very well captured with of course finite element, but in some model, in some mechanism, in some physical problems, you need to maybe combine it or find an alternative. in multi-physics, we see a finite element can, to a certain extent, but also in some of the multi-physics problems, and we know that if we really want to go into transient and semi-saturated or partially saturated, there are some issues there as well. What is the basic principle of NPM? Actually, it's a combination of a finite element Lagrangian, I would say, background with Eulerian solution for the particles. So what we have is a background mesh, as we know it in finite element, and particles that can actually flow through this mesh. So what happens that the mesh is, so we can, if we have a load, let's say, step in our solution, the mesh as we know it, so we can solve the equations at the integration points of the finite element mesh as we know, and then all this information is then transferred to the particles that are inside these elements. And in this case, the particles actually carry all the information we need. So mass, velocity, stresses, strains are carried in the particles. And once the forces and displacements are calculated, they move to the particles start to move to a new location, and the mesh is reset. Mesh is reset, it means that we don't get into mesh of excessive mesh deformation. So it's always within the limits. And the particles keep moving or flowing through this fixed mesh. And by that, we avoid this mesh distortion, and the state parameters, as I mentioned, are captured in the particles. Maybe it's a bit abstract what I say now. Just to illustrate, we have initial configuration. I'm sorry, it was, I have to go back. It's clicking first. So we have a grid and particles inside the grid. What happened is that we calculate at the integration points, and then we move actually, so the mesh actually is calculated, and it should be deformed, and this deformation is translated to the particles. The deformation takes place, and then the mesh itself is reset, and the particles keep their new location. Here it shows an example. We have, let's say, a wall, a freestanding wall, and the freestanding wall would collapse under a certain condition if it cannot sustain the verticality in this case. And then when it collapses, you see that the mesh is actually as it is. Nothing happens with the background mesh, but the particles, they flow through the mesh and come to a stable new situation. The particles can handle one phase, but if we are dealing with multi-phase, and that can be a fluid, even a gas, then we need other particles to carry this information, and that's possible. So we can have multi-phase solutions with multiple particles that handle this multi-phasing, and they interact, of course, with each other, and the solution is comprehensive in that case. So in NPM, we can handle multi-phase problems. This is again maybe a repetition, a bit more in detail. The background mesh, it is solved first at the mesh level, and then translated to the particles, and then the particles start moving after that update. Where it is useful or applicable to use NPM, as I mentioned, it's very useful in large deformation problems, moving boundary problems. So a bit large scale landslides, so not the typical slope stability unless we are looking at failure or post failure. We used it in like sand capping in land reclamation, and we used it intensively, at least at Deltares, in monopile installations. That's offshore type of piles for offshore wind, and we actually succeeded in modeling the installation phase, which usually not handled, because we're dealing with piles, if I may say, a pile in the order of 10 to 15 meter diameter, so it's a really huge structure. And the installation effects play an important role in the loading capacity of these piles or structure afterwards. What we do in finite element in other applications, typically what we call them wished in place. So you have a structural element representing the pile. You just bring it into the mesh without any installation effects. And that's a bit different now what we can do with MPM. It started early in 2013 with a PhD thesis where it started with representing or modeling impact hammering, as we see here. So the impact process can be captured into the soil, and we can calculate the resulting stresses and strains in the soil. To give a more clear example, we did centrifuge testing at our facilities some time ago at Deltares with a jacked pile that in the early days when we want also to develop and validate MPM. Here it looks at, we have, this is the configuration of the testing, you can call it a calibration chamber, where we have actually a jacked installation of a model pile in homogeneous soil in this case. And we were looking at MPM if it can capture actually what we can measure from stresses, strain, and we did that in loose sand and in medium dense sand. This is numerically what we can get, so it can of course represent the installation effect. We can get stresses and strains in the media, and we can extract this information and look carefully, for example, near the tip of the pile, what's happening in terms of stresses or in terms of strains, if we need that. And we looked at the loose sand and the medium dense sand. And then we compare it to the experimental work. And what we have seen, we did an experiment to try to compare to the experimental centrifuge testing, with including what we call then the installation effects. So actually installing the jacked pile in the MPM and then loading it afterwards, or just wished in place. So bringing the pile wished in place in the model and then loading it. And you can see here in the loose sand, this is the simulation compared to the experiment when we have installation effects, and this is without, and the same here as well. So it's much more closer to reality in this case when we are dealing with these installation effects or with this kind of problems to have installation effects included. And we have seen that much more with the normal piles afterwards as well. We use it in other applications like design optimization in a plow, so in a cutting industry, and that can be used, of course, in civil engineering application, but also in other applications. You see, you can really model the cutting process. You can extract the forces, and this is really a complex process. You cannot do that with finite element in any case, and you need something different to be able to capture. This is very complex, and it took some time to be able to get reasonable results, and it's published as well. In the Netherlands, we deal a lot with levees and dikes, very important for flood safety. And by that also, we do a lot of research, and part of that research is full-scale experiments. So there are full-scale experiments on dike structures under loading conditions and monitoring actually the failure. So the failure is also relevant in this case. We do experiments in the lab, and we do also numerical experiments with tools like MPM in this case to look at failure patterns. And we see more and more that when we are in that domain of failure, that we can really capture the right mechanisms with a tool like MPM. I had 20 minutes, so I don't want to take more time from the other presenters. So I just gave a glimpse of what MPM is in a nutshell, what MPM can do. And I would like I have two slides maybe for ending my talk, is with a call also for action. I think it's very important to realize that advancing actually our knowledge and advancing our solutions to be able to deal with the complexity we have now, the climate challenges, with the resilience, let's say, that we want to achieve, that we need to really work on collaboration, and that's cross-sector collaboration. So having Dr. Marwan here as a regulator, having industry as you all, or Engineer Hamza, and academia as a university or research institute is very important in that regard. We need to be clear on what we do with our modeling. We know everybody works in modeling knows that rubbish in is rubbish out. We know that the assumptions you make, you can always get results more or less in finite element unless you do something very, very strange. But does it mean that you get good results? So you need clear documentation, preferably peer review. And I'm talking, of course, at important projects and serious things that you need to be sure about your results. You need to build trust on the decision making. You facilitate decision making by the numerical modeling you do. And you need to have clarity and transparency in that. What are your choices? What have you done? There's a lot of details and assumptions and tricks in the numerical modeling, and unfortunately, we only see the colors and the results at the end. So that's something we need to be aware of and do something about it. The Open Culture Initiative that I mentioned already. And again, it's about numerical, but it's a lot also about the input you use, validating your solutions, experiments, or field results, or any data you can get, and move towards actually more realistic solutions. Somehow it decides to go back every time. We have already established that numerical methods are very important in what we do and continue to be that, and becoming more important as the complexity increases. So it enables actually the work we do. But maybe it's good to highlight that there's no one size fits all. It is not advised to try to fit everything into finite element just because you have the program. I would say, please look at the mechanism you have, look at the problem you have, and always have a toolbox of numerical solutions that you can utilize to better suit your problem. So finite element in most of the cases will be good, but when you are dealing with complex problems, or problems like the one that I have presented and maybe will be presented later, then there are other alternatives and also other solutions that you maybe need to bring into the table, and maybe combination of things. So mechanism-specific modeling, as I call it here, that also improves the credibility by selecting the right approach that is tailored to the problem you have. Quantified uncertainty, better decision, that has to do with we can move to a probabilistic domain. So the more we know, the more credibility we have. We can also have parameter variability, include model uncertainty, and this all comes back in added value to the solution and to the answers we give and to the decisions we make. Combining digital workflows with cross-sector collaboration promotes safer, adaptive, and sustainable geotechnical solutions. And by that, I would like to end my talk. Thank you very much.
Thank you, Dr. Ahmed. As usual, very interesting presentation, a lot of new information, and really thank you for adding this, for presenting this part of the modeling. And I think the speaker, they will have a lot of questions, so be us with us. No, the questions will be at the end, and Engineer Hamza will take care about it, and he will be moderating all the questions for all our speakers. So I think Mr. C, if you could be patient until we complete our presentation, and then you can ask all our speakers. So we'll move forward now to Dr. Reginald. Dr. Reginald, he's Chief Scientific Officer at Rocscience. He's leading provider of geotechnical software solutions, and also he serves as a director of Rocscience in Africa. He holds a PhD in civil engineering with specialization in rock mechanics from University of Toronto, Canada. as well as he has a master's degree in geotechnical engineering from Ukraine. I think the institute name is quite difficult, Reginald, so that's why I pass it.
No
And
problem.
maybe you can say it to the audience. Just to continue, Dr. Reginald, he's playing an important role in advancing geotechnical engineering, especially in Africa, and he's integral to Rocscience Global Extension and Technical Leadership. He's a technical chair for major conferences, as well as he is a specialized and expert in geomechanics, numerical modeling, risk management in mining and civil engineering works. Originally, I think, floor for you, and you can start your presentation.
Thank you very much, Marwan. And thank you very much, Dr. Ahmed, because you laid a very nice introduction to the topic. So I don't have to elaborate some of the points too much. The name Marwan of the city in which I studied in the Ukraine is Zaporozhye. So now it's in the news for the wrong reasons all the time, but that's the place I studied. So what I want to quickly do this afternoon for the next 15 minutes is just to give you an overview of the boundary element method, which was one of the methods that the previous speaker described for us. And just for interest's sake, I'll go just a little bit into the mathematics of it, just so people understand how it differs, say, from the finite element method or finite difference, but not into the serious math, just so it gives you a good idea of how the method works, what's the magic behind it. And then I'll give you some comparisons to the finite element. I'm looking at it more from the context of geotechnical engineering, but it applies to anything civil, mechanical. And then look at some recent developments that change which one I would say better for now, or which one is more appropriate. It's not so much better, but under certain circumstances, one method dominates above the other. So we'll just get a high level idea of how these differ. So that will be my goal for today. So we'll quickly look at what numerical methods are, the boundary element method specifically, how it compares to the finite element. You could also make that comparison, for example, let's say to the finite difference. We'll look at some geotechnical applications. And I told you a little bit about the mathematics because it's quite interesting. I think anybody interested in using boundary elements should know just that fundamental aspect of it. When we use it, what are its key advantages? And one of the key things is speed. How does it compare to the finite element method today? So a little bit about Rocscience. I'm sure you all know about Rocscience. I won't talk too much about it, but we are 30 years old this year. So interesting, we are getting old. We are 30 years old. Today, the head office is in Toronto, and we have some offices around the world, Peru, Ghana, Australia, and Vancouver. All right, so what are numerical methods? Many civil engineering problems are complex. You have irregular foundations, you're dealing with structural engineering, complex frames, nonlinear material behavior, time-dependent loads. And often with these sophisticated structures, we cannot use closed form solutions, neat analytical equations to solve the answers. Either we can't get exact answers, or even if we can, it's going to be extremely difficult to get those answers. So then comes the numerical methods. As someone put it, they are smart approximations using the computer. So today we use a computer to do all of this stuff. When formulas can no longer be used, how do we apply an approximate method? What they almost always do, and Dr. Ahmed gave us a good introduction in his talk, is they reduce a continuum problem, a problem where everything is continuous. There are no discrete particles per se, and simplifies it with one in which we can split the problem into discrete blocks, and then the interactions between these blocks will still approximate what happens in the continuum. The key is we get an approximate answer that is good enough. In mining, they love using the term fit for purpose. So we are looking for fit for purpose. So anytime you use a numerical method, you know you're getting an approximation. And again, the previous speaker made it very clear. That's why you check your solution to make sure your answers are good. They are fit for purpose. So always have that in mind. There's no tool that just magically always gives you the correct answer. You are the user setting up these models. You can sometimes set it up incorrectly. You will always get beautiful pictures. But as Dr. Ahmed said, is that going to be useful? That is why this is very important when we are using numerical methods. How we set up the methods, the assumptions, all the stuff, the input parameters, extremely important. Without that, we will do a very bad job. Now, this is just a simple picture for structural engineers. You have an I-beam, you have the flanges and the web. It's loaded, it's deforming. You want to know the stresses and deformations of this beam, for example. You can use these numerical methods to do that. So you split up something which is a continuum into these elements. And so we'll see the difference between a boundary element and finite element. But whatever it is, it always involves splitting up your original problem into elements, discrete particles or blocks that interact with each other, and solving some equation. You get to understand how strains, stresses, displacements, pore pressures, depending on the problem we are dealing with, vary over the structure. And as you can see, with all of this detail, we cannot use analytical solutions. So a numerical method will allow us to solve this problem. Now, I'm sure we all remember way back then when we were doing some undergraduate math or high school math. The idea behind these methods is, for example, you have a complicated function as you see drawn on this chart, and the goal is to approximate the area under the graph. Now, one of the simplest ways to solve it is if you were to split this into trapezoids, then the area of the trapezoids, when we sum them up, it's an approximation of the area beneath the curve. And we can see from this picture that if we want a more accurate answer, we just have to discretize or split the area beneath the curve into more bins. And that the more we split the area into bins, the more accurate the sum of the trapezoids get to the area underneath the curve. Because and we can always see that there will always be a little bit of an error because we'll never fully capture the entire region underneath the curve with these approximations. But the idea is good enough. If the answer is within, let's say for practical engineering purposes, 1%, 0.5%, something like that, it's good enough. So that's what we mean when we use these numerical methods. So now, anytime you have a domain, so here we have a domain, we are looking at the picture in 2D, it's always easier to visualize it in 2D. So you have a domain of comprising some material, and now you want to solve for stresses and displacements in the material when you apply loads somewhere on the boundary, or loads within the material itself. That is the engineering problem we have. Now, when you use the boundary element method, what it allows you to do is you only have to represent the boundary of the problem with elements. Once you've set up that system, you can solve that system of resulting equations for what is happening along the boundaries. So you get the boundary stresses or displacements, whatever it is, you get it. Now, knowing those values, you can calculate what is happening anywhere within this material from the solution that you came up with when you solved for the boundary stuff. So that's the boundary element method. So as you can see, if this was a real problem, we're looking at this will be one element, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements or so will allow us to solve this problem. Remember, after we get a solution, if we need answers for any other point within the solid, we can get that value based on that solution we came up with. Now, finite difference method, same domain, but you split it up into these rectangular regions, and then you can solve for what is happening. So again, if you want a better approximation, you have to use more blocks. The smaller you make them, the more it fits the region, and you can solve for that. Finite element method, in this particular example I'm showing, we are representing it with triangular elements. So we can see the difference between the boundary element method and the finite difference and finite element method. Here we only have to discretize the boundary. In the finite element and finite difference method, we have to discretize the entire domain. So we end up using more elements. Here we probably have about, on the order of about 30 elements. Here we had 10, something like that. So typically in the boundary element method, you use fewer number of elements than in the finite element method. But as an overview of how the methods work, this is just a quick overview. Now, what is the boundary element particularly good at? Like we said, because of the way it works, and I'll get into the math just a little bit, you have some assumptions regarding the nature of this material, the characteristics of this material. So if it's in the domain of solid modeling, material modeling, typically you consider the material to be linear elastic. It's the simplest formulation you can come up with. In the real world, sometimes it is non-linear elastic. It can be non-linear. It can be plastic, which means it fails, it yields. There are permanent deformations, so it gets more complicated. For simple materials that, for example, have linear elastic properties, the boundary element method is fantastic. So it solves it very well, because once you know the solution on the boundary, you can quickly calculate anything happening in the interior based on your linear elastic formulation. Now, for geotechnical engineering, one of the beauty or the strong points of this method is that, let's say this is the ground surface, you put up a building, and you want to know what is happening in the subsurface. Once you have this here and you use the boundary element method, essentially it assumes that this surface continues into infinity. So it takes care of we call them far field stresses and displacements. It's naturally built into the solution. If you are using the finite element method, for example, you may have to decide to model this portion of the infinite medium and split this area up into triangles and then solve it. So in the finite element, in the boundary element method, we only worry about the boundary, and everything else in the interior will be taken care of through some sophisticated math. In finite element, we have to discretize the whole domain into elements. So that is one of the main differences. Now, how does the math work? That's why I talk a little bit about the math, only a little bit. It's just to allow us to see how the boundary element method works. So essentially, imagine you have a surface and you want to compute the stresses and deformations or displacements in the interior of that material. If you apply a point load or a source, just by applying this, it causes the surface to deform, as we can imagine. And as a result of that, we get a redistribution of the stresses and strains in the domain. Now, that fundamental solution we use to do that, we call them Green's functions. So if you have a single Green's function, you can integrate and find out what is happening in the domain based on that solution. Now, if you are dealing with a real world problem, so you have a foundation, so you have this distributed over an area, then it's like using several of these fundamental solutions, adding up their influence, and then that allows you to determine what is happening within your elastic medium. So that's how the boundary element method works. So it's based on these Green functions, and there are several different types of Green functions. This is the typical Boussinesq solution. You apply a point load on an elastic half space. And if you put a line load or a load spread over a footing, you just discretize that area into elements, and then you can do the integrations and add up the effects to find out what is happening within your medium. There are different solutions. This is the Mendlin solution. So you have an elastic half space. You apply a point load somewhere in the medium. It will allow you to calculate stresses and displacement at any point within the medium. So that's what the boundary element method is built on. These fundamental solutions that you have to integrate and superimpose. So if you have several of them, like I drew before, you apply several of them, and you will essentially, if we are interested in what is happening here, we combine the effects of each of these loads, integrate, and we'll get a sum total of what is happening here. So that, in essence, is the boundary element method. It allows you to only model the surfaces or boundaries. Anything within the interior you can handle with the math, and hence also some of its limitations. The behavior of this medium has to be very simple, not very simple, linear, elastic generally, if we are doing solid mechanics, for you to be able to easily already calculate the stresses in between. The moment you have, let's say, for example, layered material, different soil layers, now it's not linear elastic. Even if each of them are elastic, it's not a homogeneous medium anymore, no longer. It is heterogeneous, and therefore the math, that simple math, no longer works, and then the boundary element method loses its beauty. It can still do it. There are complex formulations for handling that, but then the complexity of the math renders it way more it's much easier just to use the finite element method or something like that. So, you divide your foundational area into tiny squares, you load them with these solutions or point loads, and then you integrate to find what is happening within the domain, and then you add them up for all the different tiny squares you have. So let's say this is an underground power cavern, and we want to model it. If we are using the boundary element method, all we have to do is, this is the geometry of the cavern. The surfaces of the cavern we will fill with these elements and solve. That's it. And anything happening in the interior of the rock, we can calculate based on the solution we found for the excavation boundary. So here is a complex or more complicated mining example with excavation tunnels, stuff like that. Originally, we solve for stresses and displacements around the excavations. Once we have that, if we were, for example, to specify this plane, and it's actually divided into grid points, and we interpolate, now we can find what is happening on the plane. So this is how the boundary element works. Like we said, the finite element method, you have to discretize the entire domain into elements. Boundary elements, you don't do that. So here is just a quick example. If it's the finite element method, in this 3D, in the solid, I have to populate the whole domain with elements. I have to limit the boundary up to a certain region. The further out I go, the more accurate my results become. Here, if this was the surface, I don't have to worry about going into infinity. It's built into the solution. It takes care of far field quite readily. So that's these are the main differences between the boundary elements and the others. We can apply them to shallow foundations, tunnels, and caverns, retaining walls, seismic response. Very broad applications for the boundary element method. We don't need to know too much about this. The fewer the elements, the more coarse your results. It has fewer elements than generally the boundary element method, so it's quite useful. When to use it? Linear, elastic, homogeneous. Infinite or semi-infinite domains, I've spoken about all of that. It's very accurate on the boundary. So, for example, if you're dealing with crack problems, and I know the previous speaker alluded to some of that. If you are looking at the propagation of the crack, stresses at the crack tip, the boundary element method, it is fantastic because it allows you to, because of the math, allows you to accurately calculate what is happening here. If I want to do it with a finite element method, I need to heavily mesh this area for me to even have a chance of properly modeling what is happening here. So it has its uses. I've spoken about all of these. It's just a summary table. We're almost at the end. In the 1990s and the 2000s, where memory was a big constraint, the boundary element was very attractive. Today, because large memory is quite cheap, and in the finite element technique, there are all sorts of techniques to mesh your domain. Now the two have, even in terms of speed, the finite element has actually become faster. So the boundary element was faster in those days particularly because of memory issues. Today, the finite element generally is faster because RAM is cheap. However, there's always progress. So people are working on the boundary element method now. It's now the fast multiple method that allows the boundary element method to also do things very fast. It still has certain limitations. It's like every method has pros and cons. So for now, this is what I wanted to discuss about the boundary elements method. I'm done, and I hope I haven't gone over my time, but I'm sure you have questions at the end, and we can answer them. Thank you very much.
Thank you, Dr. Reginald, for the interesting presentation. And for sure, as I mentioned previously, Engineer Hamza, he will be moderating the session, and the closing remarks and all the questions will be at the end of the session. Now we'll move to our third keynote speaker, Dr. Ahmed Khalil. Dr. Ahmed Khalil.
Hi, can you hear me?
Yeah, we can hear you. Yeah.
Very good,
So
very good.
So Dr. Ahmed Khalil, he's the director of the engineering in Applied Science International, North Carolina, United States, USA. Dr. Khalil, he's a professional engineer with more than 25 years of experience in structural analysis, design management, and performance-based design projects, and forensic engineering and the seismic analysis, and dynamic analysis and demolition analysis as well, vibration and blast analysis. Dr. Khalil, he acts as a project manager for more than 100 major demolition projects all over the world in the United States, Canada, Brazil, KSA, United States, and Australia. Dr. Khalil has invited in many as a keynote speaker and guest lecturer in many engineering society and universities, several conferences, guest lectures, United States, Canada, Australia, and Brazil, and the Middle East, as well as he is mainly presenting about demolition analysis, progressive collapse analysis, and extreme loading as well. Dr. Khalil, he's a member of the Structural Engineering Institute, DI, as well as the American Society of Civil Engineering. So, Dr. Ahmed, please, the floor for you.
Thank you. Thanks very much. So, I'm a structural engineer by training. I will try to show the common points that I see between the applied element method and the applications for geotechnical engineering. So first, just why did the applied element method AEM come? The reason is modeling of collapse, prediction of collapse when subjected to extreme loads. The method originally started trying to study collapse initiation and collapse progression, and trying to bridge some of the missing components in finite element. We see structures performing at levels that it is hard to predict. This structure is losing 2 columns and it does not collapse. This structure is losing like 1 wall here and we have a progressive collapse. This structure is losing the whole facade, but the structure is standing up. During the session, we see structures losing multiple columns and the structures are still not collapsing. So studying the behavior of the structure when subjected to this type of extreme loading is the reason.
Dr. Ahmed, just check your voice a little bit.
A little bit higher?
No. Yeah, make it higher and try to check the connection.
I think the issue was when he played the video, it was contradicting his voice.
Okay. So you can see the video, but when I'm speaking, the voice is breaking up. Correct?
Exactly.
Okay. I'll take that into consideration. So the AEM method, applied element method, started in the University of Tokyo in 1995. As research intensified after the Kobe earthquake in Japan. But then this method was verified actually in hundreds of real-life projects trying to study the collapse of structures. We started doing preventing the collapse of structures, but over the years, my company is called ASI. We studied the intended collapse of a lot of structures in the demolition industry. So just a little bit of background. So the AEM, the idea was when it first started is to bridge the gap between FEM, finite element method, and discrete element method. The idea is in the finite element method, when you reach element separation, when you reach debris and collision, it becomes challenging, it becomes time consuming. The discrete element method, when you are in the area where you're static or elastic, it is challenging. When you have separated elements, it works perfectly fine. So the idea was to find something in between to kind of bridge that gap. So that was the concept. And I wanted to start from the end, just show you what we can do now with the applied element method. So this is real life modeling that was done in blind test mode, meaning that the pictures on the right were produced before the actual collapse of the structure that you see on the left.
Dr. Ahmed, try to explain after the video because of the problem.
So what I'm saying is, what you see is the current state of the art for applied element method. We are able to model full structures and study their collapse and estimate the mode of collapse, the possibility of buckling, etc., ahead of the actual collapse of the structure, and we are able to compare. So if you can see if you were able to see my video, Dr. Marwan.
Sorry. Yes, we can see the video.
Okay, so I'll show another one and be silent while the video is showing. So this structure was actually in Abu Dhabi, Mina Plaza. And what I'm saying is all those are blind test cases. Basically, we are performing the modeling before the actual collapse happens. So the idea is to have a tool that can model collapse, that can model impact, that can model separation of elements. So first I'm showing you what we're doing with it, and then I'll go in reverse and show how this was implemented. So here we're predicting the forces that will cause the structure to collapse. And based on that, we tell the demolition contractor how many excavators are needed to bring the structure down. And here, this is the impact of the structure with the ground. This is where we go into some sort of soil structure interaction on a different level, maybe. Can you still see my screen? Maybe I will stop the video to improve the quality of the connection. And now this is coming maybe closer to the areas that are more interesting for geotechnical engineers. We're studying impact of structures with the ground and the effect of that on underground utilities. So this here was the impact of a stack structure during demolition and the effect on underground utilities and the use of soil berms and additional protection measures to protect the underground utilities. So I went in an inverted way, starting with the final outcome, and now I'm trying to show how it all started. So in the finite element method that we're all familiar with, we have the deformation happening inside of the elements. So as you put tension on this column-like structure, on this bar, the structure, the elements become longer. In applied element method, as you pull tension, deformations happen on the surface between the elements. So deformation happens in what we call as surface springs that are connecting the elements together. This is one of the main differences between the concept of finite element and the concept of applied element method. In finite element method, we have what we call smeared crack approach, or we have to specify the crack ahead of time with a discrete crack approach, or we can use in finite element method what we call element erosion, meaning that the element disappears, is removed completely from the analysis. So if you study the collapse of the structure like that, for example, using LS-DYNAT software, to do it using element erosion, during collapse, you are removing elements. So basically, the structure is melting like an ice cube. It's disappearing as it's collapsing. So that's the techniques that are out there for modeling of separation and collapse at this type of extreme loading. In comparison, in the applied element concept, the applied element method, the idea is all the surfaces between all the elements are automatically crack surfaces. And the idea is you need to mesh the structure to a fine mesh, and then the crack will automatically be created in a way that matches the real life crack, because all the surfaces of all the elements are considered suitable boundaries for creation of cracks. By default, the method itself is doing that. So the idea is for a finite element model of a structure, as the structure collapses, it will deform like that. But the creation of separation is challenging. It can be done, but it's challenging. For the extreme loading or using the applied element method, the creation of the crack is basically automatic, just based on the mesh that you're choosing for the structure. So that is the idea behind it. And as I mentioned, it started in the University of Tokyo in the late 90s, and we're dividing the structure into elements, or the soil into elements, and we are connecting the elements using springs. So the springs on the interface between the elements represent the stiffness of the structure, and the behavior can be linear or non-linear depending on the material model. If we have additional materials, rebars, for example, or reinforcement of any type, we can add additional springs to represent the reinforcement. If we have impact or contact, springs are created automatically between different elements as they come into contact. So the key word is springs. Whenever two elements touch each other, springs are created between them, creating the contact. But it's automatic for all elements, it's built in. The other point is the number of degrees of freedom is much smaller, 6 compared to 24, for example, if you're using a finite element 3-dimensional cube, which means that we are representing all the stresses and all the internal forces using 6 degrees of freedom, meaning the number of equations is reduced. So I'll just go to a quick example to show the value of that. This is a study of the Pine Gold building that we did with the European Commission in a joint research project with Fraunhofer Institute. They were using the finite element method to model this collapse, and we were using the applied element method. But to do it properly, you need to include all the details. This was a well-documented case. We knew all the information about the steel sections, the concrete sections, the changes done to the structure over the years. And this is the result of it in short. In the middle is the applied element method analysis, and to the right is the finite element analysis, and to the left is the real life collapse. The idea is, with the reduction in the degrees of freedom, it is possible to make this analysis within 4 hours using a regular PC, while it takes approximately 15 days to do the analysis using finite element method on a supercomputer. So the challenge is how to do the collapse modeling, how to perform refinement of the collapse modeling within a practical time frame. So that's how it started, and that's the kind of advantage that we have with the finite element method because of the reduction in the number of degrees of freedom for every element. And with that, you can perform additional studies, change the material models, make sensitivity analysis, see what changes in the material model, how they affect the results, and get a more accurate representation of the separation and collapse behavior of the structure within a practical time frame. This is another example. All the examples I'm giving are like scale testing. So the idea is that it's a relatively large structure, and we're looking at.
Sure. While the video, try to speak after the video.
So here what we're showing is, will the collapse of the top floor cause the collapse of the bottom floor? Again, we're trying to predict collapse. So we're predicting how many columns need to be removed in order for the collapse to start. This was done in blind test mode. And then based on that, we're also trying to predict whether the bottom floor is going to collapse or not. So we're evaluating the impact of the structure on the rest of the structure and on the ground. So what is done differently? Because of the efficiency, the numerical efficiency, we are able to model details. If you have precast, pre-stressed slabs, we are able to model that. If you have masonry, we're able to model that. If you have steel structures with different mesh, the technique is flexible with the meshing. The meshing does not have to have full compatibility at the nodes, and because of that, you have more flexibility. You can have coarse mesh next to fine mesh without issues. You can go to that level of detail, modeling every bolt. If you have a missing bolt in a forensic study, you can model the missing bolt. You can model even the interaction with non-structural materials such as the window frame and the glass window. You can model the interface between concrete, masonry, and between brick and brick using mortar joints. You can include block separation and interaction between blocks and steel. You can model the interaction between stone and masonry and wood. And you can deal with fine mesh next to coarse mesh in the same model. You can model explicitly steel reinforcement. You can model explicitly composite sections, include springs for the steel and springs for the concrete. You can model existing structures which have strange details, mixing steel, concrete, and masonry in the same structure. You get more realistic evaluation of the behavior. And because of that, you are able to study full structures, see the shape of the collapse, and predict a collapse shape that matches reality. In this specific case, this is a case we've done 20 years ago. And in this case, the accident happened first, and then we did the analysis. All of the other cases I was showing earlier, we did the analysis first, and then the collapse was induced because it's a demolition case. This is a forensic case. The accident happened first, and then we're trying to match it based on the simulation. It's been used in universities worldwide to study and design full-scale collapse cases. So this is the collapse case that was modeled, and this is the actual collapse shape, and this is the simulation for the same collapse shape. You can model the rebar and the pulling out of the rebar from concrete. This is another full-scale test that was done at the University of Valencia. And here they are studying a two-story structure and subjecting it to column removal scenarios and estimating whether collapse is going to happen. First, this is a case with a lower load. And in this case, they remove the column, but the structure does not collapse. And then they do another one with bigger load and bigger deformation. You can see the deformation here, and same behavior was predicted in the applied element model that was done ahead of the full-scale test. And then they went with even higher load, did the same thing, and then they went with much higher load to induce full collapse of the structure with two columns removed. And this is the simulation that they did ahead of the time. This was done by the university. And then they actually went and implemented the same case. So again, this is in blind test mode. They're doing the simulation first, and then they are actually doing the test. So the idea is you have the ability to model the full structure and at the same time be able to include minor details that affect the behavior, whether the details of the reinforcement or the nonlinear behavior or the type of loading. So to get to a case that is more interesting for geotechnical engineers, this here is, I'm getting close to finishing. I'm not sure what's the time, but I'm close to finishing. So this is a case here where we are studying the demolition of an offshore structure. This is a dry dock, and we are looking at the sensitivity of the nearby structures in the dry dock to the impact due to the drop of the structure on the ground. So because we have a model for the structure, we are able to estimate where the structure is going to impact and what is the expected impact force. So again, this is done in blind test mode. The simulation on the right is done ahead of the actual drop. And because we know where the structure is going to impact based on the simulation, we can decide where to place protection to protect the dry dock. And we can also estimate the vibration. And I'm going to come to that. So we build a combined model now. Not only are we modeling the structure, we are also modeling the soil layers below the structure. And we are getting the impact from the structure onto the soil layer in the same model. And of course, because we have variability in soil properties, yes, we may have an estimation of what is the different soil layers for this specific area. But of course, there is a lot of variability. And because the technique is numerically efficient, we have the ability to run a series of sensitivity cases with different soil properties, different assumptions about the soil properties, different assumptions about the soil layers, and use that to get an order of magnitude estimate for vibration at different locations surrounding the structure. So the idea is based on the sensitivity analysis, and we've repeated that for multiple projects, the same concept. So the idea is this is also another real life project where we had nearby structures and we had limitations on the peak particle velocity for vibration at those locations. And what we can do is to solve the problem of uncertainty about the soil layers is to get the best information that we can and then perform series of sensitivity studies looking at what is the maximum expected vibration so that we can use that for design of the collapse to make sure that the structure is not subjected to vibrations that exceed the limit allowed for the structure. This is another project where we did the same thing. So the same concept again, we repeated the analysis multiple times with different soil properties. We're modeling the soil and the structure in the same model. Then we had another, this maybe will be the final case so that we do not exceed the time. Soil structure interaction. Is this soil structure interaction? We had a bridge demolition and we're trying to design the berm so that the impact with the ground is not excessive. so that dropping the superstructure of the bridge does not cause the collapse of the piers. So again, we did sensitivity analysis with multiple berm sizes, and we changed the demolition scenario different times in order to get to a case where this impact does not cause that pier to collapse. And this is the analysis that we provided ahead of the actual drop. And the idea is to include the soil model, the protection berm, and the piers, and study the collective and make sure that the impact here does not cause the pier to collapse. Earlier designs would cause much higher impact. With changes in the berm size, we came to a solution that optimizes the demolition technique. So this is just comparison of still shots. So with that, I think I've exceeded my time. I hope I didn't, but I'll stop here and to allow some time for questions.
Yeah, thank you. Thank you, Dr. Ahmed. Really very interesting, and bring to our, and different places in the world how they work. We did similar one, but we did it from the geotechnical point of view. And now we will open the floor for the question. First of all, I want to allow Hamza to moderate that session, and as a small introduction, who knows Hamza Al-Hashimi. Hamza, he's a geotechnical engineer, and he's soon, inshallah, he will be a PhD in geotechnical engineering. He's doing his PhD in IIT Bombay in India in soil structure interaction, and he's the vice president of the civil engineering section in the Society of Engineers, as well as congratulations, Hamza, for having the best project or the best research with Bentley in infrastructure recently, I think last month. Correct me if I'm wrong, and as well as he's very expert in micropile, especially in soil structure interaction with micropile. So Hamza can take the floor and moderate the remaining part of the session. Thank you, Hamza.
Thank you. Thank you, Dr. Marwan. Thank you, everyone. Where to start? It's a really interesting session. I can see we have 400 registered in this session. Maybe because of the time zone difference, not all of them is here, but of course, all of them will have an access to the recording. We have 80 almost consistently watching from the start of the event till now, which is a very good sign, and I'm sure they are all interested to know more and more about the interesting topic, which I'm sure, at least for many of us, changed the narratives about numerical models. I can see some questions, and maybe more will come into the picture while we are taking them. Let's see how we can cover. I think the first question addressed to Dr. Ahmed Elkadi about the NBM, maybe from C or so. And I can see you have responded, but maybe for the good benefit for the public, Dr. Ahmed, if you can highlight this, how NBM performs on some general benchmark cases like consolidation or slope stability, not necessarily for large deformation problems.
Yes, thank you. Yeah, indeed, at least I shared the documentation where the validation manual actually covers some of these basic cases. So, I mean, it is done, and you can see that in this validation manual. So, of course, it is intended use is large deformation, but of course, it has to perform correct in the small deformation range. So I don't know if there is other question related to this, or the information I shared is sufficient.
I think it responded, it helps, so hopefully it answers the question. Another question from Hagos Iman, any relation FBM may have evolved or developed from GeoPIV?
No. If I understand correct, GeoPIV is not a numerical method. GeoPIV is an image analysis. If that's what I know, it has to do with more experimental measurement. because we apply PIV in our experimental facilities, of course, in some of the application, particle image, and that's more image analysis related, and we're talking NPM is really a numerical method. So they're not related. Well, PIV can help in some validation cases, but there is no relation with GPIV, whatever.
Another question from Bilal Muhammad. He is a PhD scholar working now on Levy stabilization and embankments. And you mentioned this, Dr. Ahmed, but I think this question can be also for all the speakers. Could you please comment on the suitability of finite element and different numerical methods for modeling large deformation and failure mechanism in such problems?
To me to start, or
yeah, please.
Okay. Yeah, again, as I mentioned, I think it depends. If you're looking at onset of failure, I think you can tackle that with different methods, including finite element, but others maybe even limit equilibrium if you wish. But when you're talking about large deformation and failure, then I see one of the methods indeed is NPM, has been used, and the link to so just to mention, there are different NPMs in the world. So NPM is the method that I presented today. I didn't present a product or a software. We at Deltares, we have been one of the co-founders of the open source community and software Anura 3D, together with other universities. And the link that I've shared will refer you to this open source Anura 3D. Of course, each of the institution might have its own version afterwards, more refined, more enhanced, whatsoever. And there are other ones that are available in the world. So NPM is just, we don't have a commercial product or a product that I can refer to. So you need to look which ones are available. Anura 3D has been used for levees and dikes. And there are examples, even on the YouTube channel, you will see of that. So it is suited definitely for this, and we have been applying it, but I'm sure there are others, and maybe the other speakers would like to comment on that as well.
Thank you, Dr. Ahmed. Maybe, yeah, Hammah, Dr. Hammah.
I guess a very quick additional contribution is that in the finite element formulation, there are two, call it main classes. You have small strain and large strain. So large strain finite element analysis can look at large deformations. The essential difference between these two is in small strain, when I drew my mesh, whatever your starting configuration is, the neighboring of the elements does not change. If at the beginning element 1 had 3 neighbors, 2, 3, 4, they will remain its neighbors throughout the analysis. That's small strain. If you allow a rearrangement, so element 1 can now move and become neighbors with a different set of elements, that's more large strain. And there are finite element formulations that can do that. That's all I wanted to add.
Great. Before maybe to ask Dr. Ahmed on this, if he has anything to add. For you, Dr. Hammah, I just want to ask out of curiosity, why you call the BEM software you have in Rocscience EX? Does it mean that you are using it more for excavation problems?
That's it. It's for excavation analysis.
Okay, so this is where it is more useful?
So, yes, it's used for excavation analysis, yes.
Thank you. Dr. Ahmed, do you have anything to add?
No, this is clear, and indeed you can try to do large strain. We mentioned remeshing, so applied. You can also attempt to do remeshing with finite element. Again, at certain moment you will hit a limitation somewhere, and it is also not that straightforward even with remeshing. So again, it is an alternative. And again, I say you have a toolbox of tools. Look what suits the mechanism and problem at hand, and try to use that. Don't just to try to fit everything in one or the other solution, because there are more, and it doesn't work if you want to fix always with, for example, finite element in this case. But there is nothing to add. Of course, it exists definitely, the large strain possibilities. Yes. Thank you, Doctor, for adding that.
Thank you, Dr. Ahmed. And I think,
So
Dr. Dr. Ahmed Khalil, I know the most interesting part for the geotechnical engineers was the last part of your presentation. But even as geotechnical engineers, to be honest, we see the value of the AEM. And I think we did discuss before on some projects in Saudi Arabia where they have a basement and the impact of collapsing the basement on the soil and the deformation, the dust control, the ground anchors, pre-stressed ground anchors, and how they might bone us out. So maybe you can comment on that as well on such
Yeah.
applications.
Yes. So when you have separation of elements and as you mentioned, the elements are not connected to the same elements that they started with at the beginning, the applied element method becomes really valuable. So you are able to address the contact between elements. You are able to address that the elements separated and are now coming into contact again. So this aspect of it is really efficient with the applied element method. So it's one of the ways that you can handle problems like that.
We have another question, but maybe one more question for you, Dr. Ahmed Khalil, about the soil models. What kind of materials or constitutive models you are using to model the soil? Is it linear elastic? Is it?
We have the ability to do both. We've actually done both. This is where I'm speaking about sensitivity. So here we're using. You can clearly see that it's a non-linear model because you can see the damage to the soil when it hits when there is impact. But we've also done it with linear elastic models for the soil. So we've done both of them. This one had like a non-linear component so that you can study the separation or the breaking up. And again, I realized that, of course, this is an approximation because the soil behavior is much more complex. But the advantage is that the technique is numerically efficient to the extent that we are able to do sensitivity analysis. And with multiple cases, what we've done is we've obtained, based on the first real life test, we've obtained numbers that are giving us more confidence when we're dealing with a second case and a third case, especially if it's at the same site. But also we found that the experience from the impact and the vibration monitoring at one site is transferable to other sites which have somewhat similar characteristics. We're able to have more confidence every time we predict the vibrations, and we've had cases where the structures are very close by and we're able to get good estimates for vibration. And we've had cases where the structures were quite removed from the structure, but still they were sensitive. And in this case, the soil model is much bigger. So for such a big model, we would go to a linear elastic. That's to address, and in that case, that it's justifiable to use a linear elastic model because we're speaking about a really large volume of soil, and the level of vibration is low.
Thank you. I think Dr. Marwan, you raised your hand. Maybe you want to add something.
Just a quick question, and I want to check with Dr. Ahmed Khalil. Thank you for interesting presentation. And basically, we had, but the same problem here. We are simulating demolishing of the building, and what's the more problem is related to the ground. But we followed a little bit different approach by simulating the falling down of the building itself and try to get the forces, and after that applied in geotechnical model. At that time we used MIDAS. After that we get our peak particle velocity, and we check it with the impact on the building surrounding, and as well as on the bridges. And we checked even though how it's the size as a forces, if this will be accommodated by infrastructure. if this approach is widely used, or what do you think about it with compared to the approach which you use it? This is one. Number two, I think different soil model is creating many different things. For example, the speed of the PPV will be increased when you use hardening soil model, for example, and it depends on the soil. So there is a lot of details on that. So I want you to comment in the first and the second question.
Okay. So for the first point, that is very similar. The challenge that we see is like the second part, where once you have the forces and you apply them to, say, a Midas model, as you mentioned. I think it's very similar. The challenge is getting the forces. So my experience has been that traditionally the estimation of the forces coming from the impact on the ground is usually done in somewhat simplified manner, because practically speaking, I still have not seen a tool that can do the modeling of the impact for a complex structure within a practical time frame. But if the structure is somewhat simple, or the height of the details of the structure are not difficult, or the impact is happening just one impact. So I'm curious about the type of structure you were looking at, Dr. Marwan. Like, what was it?
It was 7/8 floor, and we just simply falling, because it's a big space, those are falling down. So we have to design the impactment design, which is the building should be, and we have to control the PPV velocity and to be controlled. At that time, we work it from geotechnical point of view, because we want to design the embankment, or the where we have the amount of sand and the level of it. Yeah.
That is very, very similar experience. So you were using like a nominal size, like, for example, a mass of a certain weight that is falling from a certain distance, and getting the impact based on that. So you're kind of using a nominal sort of prescriptive. We are going to allow this mass, no bigger than this mass, to hit the ground. Is that the way you were approaching it?
Yes, exactly. So this is the one. Yeah.
Yes, and in that case, that's a perfectly good way to deal with it. What we have challenge with is when we do not have control, when you have a complete collapse or an induced collapse, and you cannot control what is hitting where. You have to predict what is hitting where. If we have controlled demolition and we're dropping a piece, and the maximum piece to be dropped is this, then definitely this approach you're describing is perfect. In addressing the second point, when we're speaking about the different soil material models, again, same challenge is faced by all numerical techniques. The way we go about it is we allow for multiple material models to kind of see a range of expected behavior. So whatever the material model that you have in mind, we have the ability to model it using the applied element method. The question is how many different material models can we try within a practical time frame? So that is again the challenge we're all facing.
My last question: did you try to do an interaction between two different software? For example, the software which you saw, you get the forces from it, and just take it and just send it to the geotechnical model and try to do this type of interaction
or
as
coupling,
integrations, similarly as we are doing for the buildings and the soil structure interaction for the buildings. Yes. And
yes,
if it is more accurate or not.
What you're describing is like perfectly fine, and we have the ability to import from other tools, and we've done that in some applications, maybe more for blast loading and also for wind loading, importing this kind of loading from other tools. But for impact with the ground, because it's a structure hitting ground, so it's faster for us. Just that's the way we are we are set up, it's faster for us to use both of them are models in AEM rather than to mix up an FEM model with an AEM model, because we already have the ability to build both of them. So we normally import from other tools the impact or the loading when the tool that we have doesn't really address the phenomena that we're studying. That's more when we're dealing with like blast behavior or wind tunnel results or wind loading that's obtained from CFD software, that kind of tools, this type of tools where it's not built in our model, this one we import. But anything that is easy to model in our tool, just model it in our tool.
Thank you, Dr. Ahmed. Dr. Ahmed Elkadi, you have something to say or add, or maybe you are late. We are keeping you late.
No, I just have indeed similar to maybe the last question of Dr. Marwan to Dr. Ahmed Khalil about we have used in the past in Abacus coupled Eulerian Lagrangian analysis where you can have maybe a bit similar, so a collapse of a mast on a soil. And we had a buried infrastructure like a pipeline, and we wanted to know the impact. Are there major differences between both in Abacus and the coupled Eulerian Lagrangian in cell? You have some soil models. Some of them are also nonlinear, but they are not the advanced ones. So you have some limitation there. You need to do something to use really advanced soil models. But it can have more column and some reasonable soil models as well. How do you see the let's say the differences between both?
I'm just wondering, the question is for me or Dr. Marwan?
For you.
For you.
Me. Okay, so you mentioned a mast, so like
electricity mast.
Yeah, communication tower. Yes.
Communication tower,
yes,
electricity.
Yes.
And
yeah.
Simply collapsing on relatively soft ground with a buried infrastructure, critical infrastructure.
Yes. So again, the modeling tools for the soil are what you're describing is perfectly fine. The modeling of the collapse of the mast itself is somewhat tricky. We've done a few of those, and they tend to have the ability to collapse in unexpected modes. You can get the mast just going, for lack of a better description, it's behaving like a tree, it's falling like a tree. If you're thinking of vibration, it's the first mode of vibration, it's just rotating. But we've seen cases where the mast buckles, bends on itself, and it goes like more like a second mode or a third mode of vibration in terms of like how it's buckling, the third or second mode. And predicting that is the challenging part for me. Once you have some estimate of how the collapse is going to happen, and with different cases you get different behavior. Once you get that, then you have a good estimate of like where the impact is happening and what is the impact force. So this is where I've seen the challenge with finite element tools. For a mast, maybe the challenge is a little bit less because you can still use the truss model with a good level of approximation. When it becomes a more complex structure, it gets worse and worse. I'm not sure what's your experience with the mast model? Was it really easy to get the expected collapse shape?
Yeah, no, I think we were okay. I was just wondering if it's, for example, much faster with EM methods, or I'm just trying to figure out
if it's a truss model, there is no competition. If a truss model finite element is just the same, then like we will be doing the same thing. Like if we reduce it to a truss model, the applied element method is simply becoming just a finite element method. There is little difference. because if you're doing a truss model and you're allowing separation in finite element, then we're doing the same thing. It's the stiffness method. The worlds are meeting at this point. The different techniques are converging. If you're trying to do that model like with 3-dimensional elements and allow breaking up of truss components, then yes, you will get time savings with a technique like the applied element method. If that's what you're like the expected behavior, or that's the phenomena that you're trying to study, you will get definite savings with the applied element method. But if it's a truss model, I don't think it's justified.
Yeah, thank you very much. Thank you.
Thank you, Dr. Ahmed. And maybe we can take a couple of questions. Dr. Ahmed Elkadi, what controls the exactness or the accuracy of material point method, and maybe the calibration process of the material point method?
I don't know what to understand under exactness, so that the accuracy. So as I mentioned, it's a combination of two things. So at the heart, you have basically a finite element method calculation, and that I think is we know how it works nowadays, and it's pretty accurate. And then you have the translation to the particles and the movement of the particles, and then resetting of the mesh. There is nothing without challenge, but it has been in development for quite some time now, and I think there is of course some good validation. We have seen that it becomes problem application dependent. So every time you go into a new mechanism or a new domain, you will come across some new challenges. So it's again in the applications we have worked on, and you can find that on the ANORA website or the repository. You will see good development, and it can show that it works there. When we go out and we try to get a new, because you're always dealing with really large deformation, you're really dealing with failure. That's I think, without saying, it's not that easy to capture and model. You find challenges, and then people go back to the code and they have to do things. But in the applications domain we have now, I think it is acceptable and validated to a reasonable extent. It doesn't say that it's waterproof all the way in all applications.
Thank you, Dr. Ahmed. And another comment maybe from Mohammed Zakaria, that he wished that the session was longer because so many topics to cover, especially from you, Dr. Ahmed, the material point method. We hope the same. We know it's just a high level highlighting from all the speakers about the different methods. Maybe another question for Dr. Hammah, how we can combine the finite element with the bending or the boundary element method. Is there a software or a tool that combine, and when we use it?
Okay, we used to, I mean, even phase 2, before it became RS2, at some point it had a hybrid boundary element, finite element method. So what happens is, on the boundaries of your finite element model, you put boundary elements so you can model far field stresses. Now, anytime you do a hybrid model, the idea is to combine the strengths of the two techniques. And that is what is desired. But sometimes, unfortunately, you also combine the unpleasant parts of both methods. So unfortunately, it used to be around that version of phase 2. I'm sure if I look somewhere, I'll find it. But I think with practice, people realized that it was way more trouble than just going out far enough if you're using a finite element model or using a boundary element. The hybrid, unfortunately, sometimes inherits the worst in both techniques, not necessarily the best, although that's the goal. That's all I'll say about that for now.
Awesome. Thank you, Dr. Reginald. And for all of you, please make sure that this session is recorded, so you can access it anytime if you miss any part of the speech. Maybe some of you will have more questions. Hopefully we can answer them. We can host the speakers maybe in future events, even in conferences where we have IGIC. Dr. Ahmed Elkadi was with us last time. Maybe this time he can also join, and maybe Dr. Ahmed Khalil, Dr. Hammah. So thank you all for the great insights you have shared with us today, and thank you for the attendees. And Dr. Marwan have left. He's sorry, he has appointment. So thank you.
Thank you very much. Really enjoyed
Pleasure
it.
meeting
Thanks.
you all. Pleasure meeting you all.
Yes.
Thank you.
Thank you. Assalamu alaikum. Bye. Cheers.
Alaikum
Cheers.
salam.
Cheers.